Welcome to Z. Today, we're embarking on an incredible exploration of one of the most profound concepts in modern science, the Big Bang Theory. This groundbreaking theory not only explains the origins of our universe, but also guides our understanding of its vast evolution over billions of years. Join me as we delve into the evidence, implications, and enduring mysteries surrounding the Big Bang, illuminating the story of how everything came to be. The Big Bang Theory posits that our universe began as an incredibly hot, dense point approximately 13.8 billion years ago, often referred to as a singularity. This singularity was not a traditional point in space, but rather a state of extreme temperature and pressure where the known laws of physics break down. In this early state, the universe was filled with energy and elementary particles like quarks and electrons. As the universe began to expand, it cooled rapidly, leading to the formation of protons and neutrons within the first few minutes. This cooling allowed for the birth of the fundamental forces that govern our universe: electromagnetism, the weak nuclear force, the strong nuclear force, and gravity. Imagine the universe as a balloon being inflated, not just expanding outward, but expanding space itself. As it grows, everything within it stretches and transforms. This ongoing expansion is the backbone of the Big Bang Theory, showing us that our universe has been in constant motion since its inception. Several key pieces of evidence provide compelling support for the Big Bang Theory, forming a cohesive narrative of the universe's history. One of the most significant is cosmic microwave background radiation, CMB. Discovered serendipitously in 1965 by Arno Penzias and Robert Wilson, the CMB represents the afterglow of the hot, dense state of the early universe. It is a relic radiation that fills the cosmos, offering a snapshot of the universe just 380,000 years after the Big Bang. The CMB is remarkably uniform, with tiny fluctuations that correspond to density variations in the early universe. The average temperature of the CMB is about 2.7 Kelvin, and it was mapped extensively by missions like the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck satellite. The anisotropies observed in the CMB are critical. They indicate the seeds of future structures, such as galaxies and clusters. Understanding these tiny variations helps astronomers reconstruct the universe's evolution over billions of years. Another significant piece of evidence is the observed redshift of distant galaxies. Edwin Hubble, in the 1920s, found that galaxies are moving away from us, and the farther they are, the faster they're receding. This redshift occurs because the light emitted from these galaxies stretches as the universe expands, providing a clear indication that the universe is in a constant state of growth. Picture astronomers peering through powerful telescopes, measuring light from galaxies billions of light years away. Each redshift they observe serves as a cosmic message, confirming that our universe is not static but dynamic, continuously reshaping our understanding of cosmic evolution. The Big Bang wasn't just an explosion in space, it was an extraordinary expansion of space itself. During the first moments of the universe, in what is known as the Planck era, conditions were so extreme that our current understanding of physics breaks down. As the universe began to cool, fundamental forces started to separate. Within the first few seconds, protons and neutrons formed, leading to the creation of light elements through Big Bang nucleosynthesis. This process occurred during the first 3 minutes, when the universe was hot enough for nuclear reactions to take place. During this crucial period, about 75% of the universe's mass became hydrogen, with helium making up about 25%. Other elements like lithium and beryllium were formed in trace amounts. This primordial composition set the stage for the formation of stars, galaxies, and ultimately, the chemical diversity we see today. Imagine a cosmic cauldron filled with energy, where fundamental particles collide and bind together, creating the very building blocks of the universe. As the universe continued to cool, these particles coalesced into atoms, allowing the formation of the first light elements that would play a vital role in cosmic evolution. As the universe expanded and cooled further, structures began to emerge. Small fluctuations in density, influenced by gravitational forces, allowed matter to clump together, eventually forming the first stars and galaxies. These early stars, known as Population 3 stars, were massive and hot, composed almost entirely of hydrogen and helium. They ignited through nuclear fusion, emitting light and heat that illuminated the dark universe. The end of their life cycles, often resulting in supernova explosions, scattered heavy elements throughout the cosmos. The supernovae of these massive stars played a crucial role in enriching the interstellar medium with heavier elements like carbon, oxygen, and iron. This process created the necessary ingredients for forming planets and ultimately life. The cycle of stellar birth, death, and rebirth is fundamental to the evolution of the universe, leading to the complex structures we observe today. Picture a once dark universe gradually filling with brilliant stars, each one a beacon of light born from the remnants of its predecessors. This cosmic dance of creation and destruction not only shaped galaxies, but also laid the groundwork for the emergence of life as we know it. The Big Bang Theory offers profound implications for our understanding of the universe and challenges us to reconsider our concepts of time, space, and existence. One of the most fascinating implications is the notion that the universe had a beginning. This challenges traditional ideas of infinity and prompts philosophical inquiries about what, if anything, existed before the Big Bang. It invites us to ponder the nature of existence itself. Some theorists propose models like the multiverse, suggesting our universe is just one of many, each potentially with different physical laws and constants. These concepts push the boundaries of our understanding and spark debates about the nature of reality and our place within it. Imagine grappling with the idea that time itself has a starting point. What does this mean for our understanding of causality? Each of these questions invites deep contemplation, leading to a richer appreciation of the universe's complexities and the mysteries that remain. As our observational technologies continue to improve, scientists are consistently refining our understanding of the Big Bang and its aftermath. Ongoing missions, like the James Webb Space Telescope, are set to explore the early universe, searching for the first galaxies and stars formed after the Big Bang. The data collected by such missions allows researchers to peer back in time, uncovering the conditions and processes that govern the formation of the first structures. By studying these ancient galaxies, scientists hope to understand not just how they formed, but how they evolved into the galaxies we observe today. Additionally, researchers are investigating the mysterious components of the universe, such as dark matter and dark energy, which together account for about 95% of the universe's total mass energy content. Understanding these elusive phenomena is crucial for deciphering the universe's ultimate fate and how it has evolved since the Big Bang. Picture a team of scientists at the forefront of cosmic exploration, analyzing data from distant galaxies and colliding particles in large particle accelerators. Each new discovery is like a piece of a grand cosmic puzzle, bringing us closer to understanding the origins of everything we see around us. The quest for knowledge is unending, and with each breakthrough, we unveil more of the universe's hidden secrets. The Big Bang Theory is not merely a scientific concept, it's an extraordinary narrative of our universe's origin and evolution. From the hot, dense beginnings to the vast and intricate cosmos we inhabit today, the Big Bang has shaped everything we know and see. Thank you for joining me on this journey through time and space. Keep looking up and remember, the universe is full of mysteries just waiting to be unraveled. Until next time, stay curious, and may the wonders of the cosmos inspire you.